much, so it would be very great if you explain this.
Yeah, okay. So, yeah, I'll try to do my best. Okay. So, anything else that you would like to know? Okay. So, let us start with the combustion itself. So, when we have combustion, uh, so wh- so a combustion. So, consider we have a Bunsen flame. Usually, it looks like this. So it is a particular scenario where the flame shape has changed. So this is flame. Okay. So let us consider a flame. This is a flame where from the bottom we have unburned mixture of fuel and oxidizer, right? And at the exit we have the products. Okay. Where we have products. Correct?
Yes, sir.
Ah, so, so across the film, the temperature increases, density decreases, velocity increases, right? So here the temperature is say T naught, density is rho naught, and V is V naught. Okay, so so these three things will takes place. Okay, so so the flow will be turbulent in nature, which means that we will have some fluctuations. So velocity can be written as some mean velocity and some fluctuating velocity. Similarly, density can also be written as density mean density plus fluctuating density. Similarly, the temperature will be fluctuating temperature, mean temperature and fluctuating temperature. Okay, so when they crosses this flame, the the disturbance also gets amplified. Okay, so okay, so disturbance amplifies. Okay, density increases. Density decreases. Sorry. Yeah, and the velocity also will increase, right? So, so we can assume, we can say that this flame is some is can be assumed as a source of sound. Okay, so whatever, so source of source that amplifies whatever disturbance is there at the upstream, right? Okay, so so we have seen that now we have seen that the flame can be assumed that uh, it is a diaphragm that creates sound. So similarly, you might have seen when you switch on the gas stoves, you can hear some roaring sound, right? So that is the sounds that a flame creates. Okay, so we have a broad band of frequency. So we have a broad band of frequency where the so if I plot frequency versus amplitude, so it will be something like a broadband. Okay, so at different frequencies we'll have different amplitudes of the sound. Okay, now we have a rocket engine. Okay, let me use my OneNote. Yeah, so okay, so we have seen that a flame can be assumed as a source of sound. Okay, so when we have a rocket engine, we have injector that that creates a flame. Okay, and this flame basically has a broadband spectrum which means at different frequency, it creates a sound at different frequency and of different amplitude. Okay, so uh, so uh, so uh, at the nozzle, the flow is choked, right? And whatever the disturbance that is coming in, pressure wave that is coming in, uh, will uh, will not be able to pass through this choke nozzle. So this condition is also known as thermally choked nozzle. Acoustically choked nozzle. Acoustically choked nozzle, which means any disturbance that is coming in uh, will reflect back. In other way, it will act like a uh, closed boundary. And here also we have a closed boundary, right? Okay, so we can simplify this combustion chamber as a tube, so which has which is closed at both the ends. Okay, and so we have a sound source that is there inside the we have a sound source which is inside the combustion chamber. Okay, and it is creating sound. So, and this sound is of broadband, which is broad, as it is in broadband in nature. Okay, so what will happen, certain frequencies, the flame that is creating a sound, certain frequencies will match the natural frequency of this tube, and they get amplified. So after some time, what will happen? You'll see a if you place a microphone in this section, so what you will feel is the amplitude will suddenly increase. Okay, and so what will happen? The the unsteady pressure P naught will continue to rise. Okay, and they so so if I plot this pressure versus time, so what you'll see, there is oscillation that is increasing, and they usually uh, usually becomes constant after some time. Okay, this is known as limit cycle oscillation. Okay, so at this point, the energy that the flame is putting into the combustion chamber is getting just reflect by the outer surface. So we have a energy balance at this point, and below that the energy from the sound sources greater than what it is lost from this walls. Okay, so this so how it is dangerous for a rocket engine. So, uh, so if this pressure limit, the pressure amplitude, uh, what will happen is the pressure inside this chamber will increase, right? At this points, at the extreme points. Okay, so if my thickness of the wall is less than the structural capacity of this pressure, um, then it is fine. Otherwise, what will happen? The rocket will there will be a catastrophic explosion, and the rocket will fail. Okay, so this is the reason for combustion instability. This phenomena is known as combustion instability, and it can lead to many other phenomena. Okay, so one of the phenomena which Professor Ramamurthy has explained was, you have a combustion chamber, you have a combustion chamber, and the pressure inside the combustion chamber is changing with time. Okay, so let us assume that it is sinusoidal in nature. So what will happen? The pressure will increase. Uh, so the pressure will increase, and the pressure inside the tank, whatever is there, say P naught. So the whatever the velocity that is coming is directly proportional to the difference between this P minus P naught, right? So yeah, so so once this pressure is increased, the velocity will decrease, and eventually the mass flow rate that is coming into the engine will decrease, and this will again lead to this coupling between this combustion chamber and the fuel supply. Okay, so this phenomena is known as feed line combustion chamber coupling. So yeah, it changes whatever the mass that is coming inside the combustion chamber. So I hope you are with me, right? Um, Anirudh, right? You asked this question. You were having a doubt.
Yes, yes, sir. Yes,
So
sir.
uh, okay. So main reason is the source of sound, that is the flame that is creating a broadband uh, frequency, and some of the frequencies that are getting coupled with the rocket engine. Okay, so last time okay, let me show you an image which shows what happens when you have a such type of oscillations. Okay, so this is the injector plate that you are looking into. So you can see that the injector plate has completely melted. Okay, though you can see the injector plate is completely melted because of this pressure fluctuation, which will increase the temperature also. As the pressure will increase, the temperature will also increase. Okay, so yeah, so you can see this uh, uh, the the injector place has is getting is damaged, and you can also see the this is the thrust chamber. So the walls of the thrust chamber is also eroded. So yeah, so in this case, the whatever the pressure oscillation that was getting generated by the flame and the coupling of the combustion chamber had exceeded the structural limit of this material. Okay, so yeah, so this is the reason for the combustion instability, and Professor Ramurthy might have explained you the some derivations which by which you can decide what should be the injection pressure to avoid combustion instability, right? So according to Sutherland's law, it should be the P injection should be two times of the combustion chamber. Okay, or in the sense, PC by P injection should be half.
Sir, I didn't get this, sir.
Okay, so I hope you have seen the lecture, right? Where the professor explains you.
So
Uh,
you muted.
Hello, hello. Yeah,
No,
can
it's
you?
all right, sir.
So I hope you have seen this lecture, right? Where the professor tells
Yes, sir.
the relation like this. So the pressure increases, and the in some cases the uh, P injection the mass the pressure will catastrophically increase, right? In some cases, wherein in some cases the pressure will decrease, right? Depending
Yes,
on
sir.
the injection pressure. So with that, professor has came up with this. He told that to avoid this combustion instability, your injection pressure should be greater than uh, two times the combustion chamber pressure, right? uh, okay, so yeah, in other case, he has also derived one this analysis for a bulk mode of combustion, right? Combustion instability, where he has come up with this relation, Tc by T residence should be less than pi minus tan inverse meter square minus 1. This, I hope that you have seen this derivation, right? So this is the uh, okay, this is the characteristic time, and this is the residence time. And yeah, so this is, so beta, whatever, so beta we have said that this is PC by 2 P injection by minus PC. So we have a plot something like this. So for this case, this is TC by T residence, and this is against beta. So we have seen this, for this curve, if we are below this point, we are stable, otherwise we are unstable, right?
Sir, actually,
Huh.
I don't know if this was taken in the lecture, but I didn't get it. Like, how would this relation came? I didn't understand.
Okay, so this is
Sir,
I
could you derive it? Could you derive it if you?
yeah, I can derive it. Okay, so so yeah, okay, so let us start with this. Mm. Actually, it is there in the lecture, right? Maybe I'll share the link. It is fine.
Sir, actually, it's not there, I guess.
Um, let me, okay, let me check. So it was supposed to be there. Okay.
Sir, actually, it was there in like one part of the board. I could see this written, but
Forward
there
wave
was
from
no
which we did.
explanation for it, like for the given video in the course.
Okay. 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 Understood. So let me derive it then. Okay. So okay. Uh, okay. Let us look into this derivation now. So we have a combustion chamber. Okay. So what we are interested here is how this dm by dt changes with how the pressure changes with time. Okay, so what we'll do is we'll start with the conservation of mass, that is dm by dt is equal to m dot g minus m dot n. So we have a nozzle here, nozzle, and this is m dot g. Okay, so right, so this, for liquid rocket engine, the whatever the mass that is coming in is through the injector, whereas in case of solid rocket propellant it will be through the surface, right? So that's why we have written this g, which tells this is mass that is generated inside rocket motor. Okay, so right, so now what we can do is, okay, so yeah, so this m generated basically will have some delay. Okay, so when you are injecting the propellant, it will take certain amount of time. So 1 minute. So it will take certain amount of time to evaporate and atomize, right? So we can write this thing as mass of the propellant that is getting injected, and yeah, with some delay time t minus tc. Okay, so this is okay, this is at t minus tc, and what it is going out. Okay, so mass through the nozzle can be written as 1 by
Sir, I
cc.
didn't get. Sir, I didn't get T minus TC. Sir, why?
Okay, so what I'm saying is, at time t is equal to uh, okay, so okay, so when we inject this liquid propellant into the combustion chamber, okay, it will take certain amount of time to convert into gas, right?
Yes, sir.
Okay, so there will be some amount of delay that will be there, that is denoted
Okay, sir.
by T minus Tc.
Okay.
So mg is, sorry, this will be mg is mass of the propellant that is getting injected, and at certain delay this will contribute to the gas phase. Okay, so mass to the nozzle can be written as pc at by c star, right? And
Yes, sir.
similarly, okay, uh, and mass of the propellant can be written as cd a naught under root 2 rho p injection minus pc. So we have a tank, we have the okay, so this is p injection, this is pc. So based on the conservation of mass, if the injector area is a naught and the flow discharge coefficient is cd, so we can write the mass of the propellant as this, right? So this is the velocity by Bernoulli. Simple Bernoulli, we can write the velocity at the injector as 2 rho injection minus PC. Okay. Okay. Sorry.
Yes, sir.
This will be, sorry. This will be 2 by rho. Sorry. So mass flow rate. This is rho a naught v into CD. So if you substitute this, you will get this relation. Okay, now what we have to do is, we have to substitute these values in this equation. Now dm by dt is cd a naught 2 rho p injection minus pc minus 1 by c star pc at. Okay, but this is at t minus tc. Okay, so yeah, so now let us write this equation in terms of pressure now. So mass can be written as this is pc dt, this is vc rtc. Okay, this is cd a naught 2 rho p injection minus pc. This is at time t minus tc minus 1 by c star pc at. Okay, so okay, another thing, this okay, so let us dpc dt rtc vc. This is cd a naught 2 rho p injection minus pc. This is P minus Tc 1 upon C naught. This is PC AT. This is Tc VC. Okay, so now C star can be written as 1 by gamma RTC 1 by 2 of the under root, and L star can be written as VC by AT. Okay, so what we are interested in, we are interested in combining these terms. Okay, um, this term. So let us write the equation. Okay, so this will be okay. So this is so we are writing for this the part. So we can write this 1 upon C star RTC VC PC AT as gamma RTC divided by PC AT PC, which will give you gamma square L square. So we are combining these terms so that we can just simplify. So we do not want more variables, so we are clubbing those variables into these three gamma, C star, and L. Okay, so this is for this term, and similarly for our TC, VC, CD, A naught, 2 row, P injection minus PC, and PC is RTC, VC, CD, A naught. So now what we can do is we can the combustion chamber pressure can be written as mean chamber pressure plus some fluctuating part. Okay, so yeah, so this is 2 row, this is 1 minus um, P injection pin, this is PC. Okay, this is okay, 1 minute, so this will be there. So 1 minute, so there's a okay, so what I have done here is, let me erase this. So 2 row P injection minus this thing plus P dash. Okay, so this can be written as so this is a some involved derivation. So okay, so this is a row, sorry, this will be okay, so this can be written as P injection um, so this thing, and you will have injection minus PC by 2, and this was computed as T minus TC. Okay, so if you substitute this, you will get how the combustion chamber pressure will change. So for this type of thing, you will get a relation something like this. Okay, L star PC. Okay, so this is what you will get. So if I so so this term, this L star by C star gamma square has a unit of time. So which okay so this is known as, this is can be written as T residence. Okay, similarly, um yeah, so T residence. So if you substitute this, you will get this equation: dpc by dt minus is equal to pc by t residence. So after some manipulations, you will get this type of equation minus pc by t residence. Okay, so now what we have to do is some frequency analysis in this, and after that, uh, what we will get is this relation, that Tc by T residence for a stable combustion, the it should be less than this value. Okay, so this comes by the analysis of how pressure is changing inside the combustion chamber. So this is what we get as the condition for a stable combustion. So maybe let me do one problem, then it will be clear to you all. So okay, so we have to predict the bulk mode of instability in a liquid rocket engine. So let us pose a problem. We have a pressure fed liquid rocket engine. Okay, and the thrust chamber operates as a pressure, so PC is given as 0.8 megapascals. Okay, so the pressure drop across the injector is given, so this is P injector is 0.3 MPa. So this is the pressure drop that is given. So this the net pressure. Uh, okay. Uh, okay. Let us write this thing first. So PP injection. Okay. So this is delta P is given, that is the pressure drop. Okay, which is P injection minus PC is given as 0.3 MPa. Okay, so we have to predict whether this rocket will fail or not, and it is also given that the residence time of the propellant within the combustion chamber is T residence is given as 3 milliseconds, and combustion delay time is given as combustion delay time, that is TC is given as 10 milliseconds. Okay, and we have to predict whether the combustion instability will occur or not. So and if it occurs, and what is the frequency of this combustion instability. So for stable combustion, it is TC minus T residence should be greater than pi minus tan inverse. So if you want to follow this derivation, you can look into rocket propulsion book by Professor Ramamurthy. So in that, he has done a detailed derivation of this. So so beta is given as PC by 2 delta P, which is 0.8 divided by 0.6, which is 1.33. Okay, so yeah, so this is so if you compute this value, tan inverse beta square minus 1 half. So you will get the value as 0.235. Okay, so for combustion stability to occur, uh, for a combustion stability to occur, the Tc by T residence should be greater than 0.77 pi by 0.88. Okay, so yeah, so this is, it should be yeah, it should be greater than 2.75 for instability to occur. Okay, so yeah, so let the value for this Tc by 3, which is 3.33, which is greater than 2.75. Yeah, so this is true, which means the instability will occur. Okay, so let us calculate what should be the injection pressure for same case where the instability is not there, with same parameters. So this is 3.33, which should be greater than equal to pi minus tan inverse beta square minus 1 half. This is beta square minus 1. So what we can do is we can use our calculator to calculate what is the value of beta for this condition. So um, yeah, 1 minute, let me calculate this value. So this is radians. So yeah, pi minus tan inverse minus 1, the power 0.5 divided by square minus 1, 0.5. So let's solve this. Okay, if you calculate this value, uh, so if you calculate this, you okay, you'll get some value for beta. So let me solve this. So this is solve. This is okay. So you'll get a value for beta, and you know the chamber pressure. You know the chamber pressure for this condition. So you can calculate what is delta P across the injector, and based on that, you can design your turbo pump. Okay. Yeah. So I hope this is clear, right? So this is a involved derivation for this. You can have a look into this Professor Ramamurthy's book. So I think the chapter number is the chapter name is Combustion Stability itself, and in that he has done a derivation. So yeah, okay. So any questions on this? So maybe I'll show you some images in what a liquid rocket the combustion instability can do. So this is in a gas turbine. Okay, so this is in a gas turbine where you can see the gas turbine blades have been destroyed. And this is the injector plate. You can see the injector plate has been melted in this case, and the thrust chamber is also destroyed. Okay, so yeah, this you can ignore. Okay, so yeah, so this is the kind of injector you see in the liquid rocket engine. You can see the flame that is coming in. So we have different phenomena that is happening. This, that is the shear layer that is there. So they also create some kind of sound which can couple with the liquid rocket engine. Okay, and uh, this is the spray that is this is the new spray that is getting developed in rocket engines, that is known as spindle injector. So we do not want different injectors in the liquid rocket engine. Only one injector can help to spray the propellant in complete combustion chamber. Okay, so yeah, so let us move to this combustion stability part. uh, okay, so let us try to do some problems. uh, yeah, so okay, so we have a first question that regarding the turbo pump. So it is operating at a speed of 1800 rpm, and is used to feed the liquid propellant of density. So density is given, so propellant density is given as 975 kg per meter cube, and has a mass flow rate of 72 kgs per second, and it is fed into thrust chamber. The pressure rise across the pump is, so delta P, it is given as 5 megapascals, and a request is received to upgrade the performance of the liquid rocket performance by increasing the pressure across the pump by, so delta P1 is there, so we have to design a combustion chamber. Okay, so Raman, right? Maybe I'll discuss it in the next time. So that is a final tutorial. So this week I was planning to discuss on combustion instability and few questions which I feel it is important for your assignments. Okay. Okay. So okay. I don't think so. This is the probably the second last tutorial. After this, we'll be having one more.
Sorry, can I speak?
There will be another next week tutorial.
But assignment submission is this Wednesday. That is day after tomorrow.
Yeah, after that also you can have there's one um,
But
tutorial.
then,
Huh?
so these tutorials, they don't help in the assignment pre-hand, or they only help post hand.
Yes, exactly. So after so yeah, so whatever you have questions regarding the previous assignments, or so uh, yeah, that's why. Okay, so if you want some questions on electric propulsion, maybe I'll discuss it today.
Okay, okay.
Okay, so okay, so maybe I'll discuss few questions after this. Okay, so let us look into this problem now. We want to upgrade this pump to 7.5 megapascals while retaining the same diameter of the impeller. So if the specific speed is ns and the specific diameter nd for a turbo pump are given as, so what we have to do is we have to find the flow rate of the propellant supplied by upgrading the uh, pump. So we have to find what is So what is the flow rate we have to find? Okay, so any idea how we'll do that? So this is
So equating the specific diameter.
right. So okay, so can you try this problem yourself, and let's can you see if you are getting the value in this range, and we'll try after this.
Yes, sir.
So okay, let me uh, write this thing. So uh, l- yeah, so let us equate the specific diameter. So the delta p1 by rho 1 by 4 is equal to delta p2 by rho 1 by 4 divided by q1 by q2. Okay, so if you substitute this, so you will get the so okay, so q1 you can calculate. Q1 is m dot 1 uh, divided by rho 1, right? So yeah, so you can calculate q2. So this is q1 under root delta rho 2 delta p2 by delta p1. So yeah, so this is m dot 1 by rho delta p2 by delta p1. So with this you will get value as 0.09 meter square per second, meter cube per second. I hope you are getting this value right. Are you getting the same value?
Yes, sir.
Okay. So now the we have to find the specific speed of the pump. So the specific speed is given as omega under root q delta p by rho 3 by 4. Okay, so we have the speed omega is uh, we can calculate by rpm. So it is 18,000 rpm, uh, 60 under root so we have q dot, that is okay, so
So are they talking about the new flow rate?
here,
Yes, sir. Like
yes,
in the
in this
second
first
question.
problem they were asking for the new flow rate. So what we can equate this specific diameter, and based on that we can calculate what is the flow rate in the other case.
So like in the second, we need like, is it a part of first question? Like
Yeah,
we
second
need
part
to.
is the part of first question only. Okay, so we
Okay,
have to
okay.
find the specific speed. Okay, so Okay, this is for the pump. This is the current pump. Okay, for the current pump. Okay, then okay. So if you substitute this, you will get the value as, okay, yeah, and this is m dot 1, which is equal to 72 by 975 divided by 5 into 10 to the power 6, and this is 975 3 by 4. So if you substitute this, you will get ns as 0.845. Okay, and now what we have to find, what is the rotational speed of the upgraded pump. To find the rotation speed of upgraded pump, what we can do is we can equate the specific speed for both the cases. So yeah, so what we can do is, this is omega 1 q1 dot delta p1 by rho 3 by 4 w2 delta p by rho 3 by 4. Okay, so this is w2 is q1 by q2 divided delta p1 by delta p2 3 by 4 into omega 1. So this, when you do this, you will get the value for uh, the upgraded pump as 22,100 rpm. Okay, okay, so I hope this problem is clear, right? Okay, so let us do a problem on electric propulsion. um, okay, um, okay, so we have a so let us calculate um, so do you have any specific problem which you want to uh, you have a issue with that? Okay, so let us do for iron thruster. uh, okay, so we have a steady, so let me write the problem first. So a steady stream of propellant xenon interacts with electron in an ionization chamber to generate positively charged ions with a charge density of 2 into 10 to the power 4 coulomb per kg. Okay, so the ions are captured in an extractor grade and thereafter they are accelerated using a high velocity using acceleration voltage of, so delta v, the acceleration voltage is 3 into 10 to the power 3 volt. Okay, the current due to the ion, okay, so the current is given as 0.25 amperes. So what we have to find is, first is the exit velocity. So we have an ion chamber. So this is a screen across which the voltage is 3 kilovolt. Okay, and the current is given as 0.25 amperes, and we have to find what is the velocity with which the xenon ions are getting out of the thrust chamber. Okay, so first of all we have to calculate the exit velocity, for which what we can do is we can calculate the mass flow rate. I hope this problem is clear, right? So the mass flow rate is given as okay, so um, this is 0 point the current, this is the current divided by the charge density. This is 0.25, 2 into 10 to the power 4. This is 12.5 into 10 to the power minus 6 kgs per second. Okay, so now what we have to do is we have to okay, we have to equate the the energy that is being supplied, that is the power, which is v into I, and it will be equal to m dot vj square, right? So this is 3 into 10 to the power 4, and yeah, this is 3 into 10 to the power 4, and current is 0.25, and this is 2 divided by 12.5 10 to the power minus 6. This is vj square. So vj, with this you will get the velocity as 10950 meters per second. Okay, now we have to calculate what is thrust. This is m dot, so the next part is the thrust we have to calculate, and it is m dot into vj. Okay, so this is 12.5 10 to the power minus 6, 10950, this is 7 newtons. Okay, so I hope this is clear, right? This problem, uh, who asked, Rajan, right?
So it was Raman, I guess. He went.
Okay, okay, it's okay. So I hope this is fine, right? This question.
Yes, sir. I didn't understand the part where the ions are like the I meant a sail propulsion, like when the ions are used in a problem where there is a sheet and the ions are reflected. What is the pressure? I get
Okay,
stuck
that
on
is a
those type of
radiation
problems.
pressure, right? You are asking about.
Yeah, yeah, yes, sir. Radiation pressures.
Okay, so radiation pressure is basically the photons that are traveling with certain velocity. So if you have a solar sail, right? Okay,
Yes, sir.
so the photons that are getting are impinging onto this surface, they also creates a certain type of force. Okay, when they hit, so this force per unit area, whatever we say is known as the radiation pressure. Okay.
Okay, sir.
Okay. So if you want, let us look into some problems, maybe. Uh, Let me. Okay. So so probably let us do the solar cell problem. Huh? Okay. So let me remove this. Okay. So let us look into the solar cell problem. Yeah. So a solar cell are the method of the spacecraft propulsion using radiation pressure exerted by sun on the large reflecting material. A solar cell powered spacecraft does not need a traditional propulsion system for the power, because the propellant is, this is just a description what a solar cell is. Okay, so what we have, okay, so light composed of electromagnetic radiation that exerts a force on the object. It comes from the contact. Okay, so that's what I explained just now. So a group of space enthusiasts would like to apply solar cell propulsion using photon from sun to propel the space capsule. So yeah, so the energy that is coming in is given by h nu. Okay, so yeah, so nu is the frequency of and yeah, so the energy of the photons can be written as in this way, right? So energy is h nu, which can be written as sc by lambda. It can be written as okay, so this is the intensity of the radiation into the area, and it is and the time over which the radiation is received. Okay, so yeah, so the ratio of intensity of the radiation to the speed of sound means I by c is given. uh, I by c is known as pressure of the photons. Okay, so this is radiation pressure. Okay, so what we have to find is the pressure that is exerted uh, by these photons. Okay, so can we okay, let us try this problem. So okay, so yeah, so the solar cell area is given. uh, okay, 1 minute. So pressure. Okay, so solar area cell area is given, which is 18.75 meter square, and radiation intensity is given as 200 to 2000 watt per meter square. Planck's constant is given as 6.625 10 to the power minus 34 joule second, and speed of sound is also given. Okay, so now we have to find the pressure. So pressure, it is given that pressure is uh, okay, so this is uh, 2 I by A, which is okay, so this is equal to 2 into 2000 divided by,
So is it 2 I by C?
yes, it is 2 I by C. Oh, I think it is means, yeah, it is 2 I by C. uh, okay, it is 2 I by C, but okay, so what we can do is uh, so So what we have to find is pressure exerted by photons on the sail. Okay, so right. So this is I by C. So this is H by lambda, which is I by C A into uh, T, right? So yeah. So uh, okay. So this is okay. This is also written in this way also, that it is two I by C. Sorry, it is C, not A. This is 2I by C. Yeah, sorry. Thank you for that. 2I by C. Yeah, 10 to the power 8. This is 0.0134 millinewton per meter square. Okay. Then what we have to find is what is the thrust generated by the solar sail. So the this 2I by C, which is equal to thrust by area. Okay, so thrust can be written as 2I by C into area. So with this you can calculate thrust as 0.251 millinewtons. Okay, so I hope this question is clear, right? Okay, any doubts up till now? You, if you have any doubt, please let me know, because we this session I'm planning.
Excuse me,
Huh, yeah.
sir. We can find the thrust by pressure into area also.
Yeah, it is
Radiation
same,
pressure
right?
into
So
area.
this is so
Yeah, yeah. Yes, sir,
this
yes, sir.
this is pressure, right?
Yes, I got it, sir. Got it.
Okay, yeah. So any doubts? Any other doubts?
Sir, I had a doubt in week 10.
Huh. Please tell. So week 10 will be
Yes,
there.
sir. So
This
week
is
10, question number 17.
I don't know the question. Please can you let me know?
Okay, 1 minute, sir. I'll just open that.
So it was related to liquid rocket propellants, right?
Yes, sir. Uh, yes, sir. It was related to liquid rocket propellants. Yes, sir. A gas-fed regulator system. I'll just copy this question and post it in the chat box.
Sure, sure. Okay, so it
Yes,
system.
sir.
Okay, okay, okay. So okay, so this is a half question, right? Following parameters.
Okay. Yes, sir. Yes, sir. I'll just give you the question. 1 minute. Let's see. Yes, sir. This is the question. Work done by helium.
Okay. Yeah. So let us draw the question first. So work done is basically the change in the internal energy of the system, right?
Yes, sir.
So okay. So let me look into my notes. Yeah. Okay. So this is so a gas fed system. So we have some gas bottle, and we have a tank. Okay, so a gas phase system, monopropellant containing helium at 30 megapascals. Temperature is 300 Kelvin. Okay, and we have hydrazine. in the tank. Sorry, hydrogen will be, this is in the, this is the helium and this is hydrogen. Okay. Um, the pressure. Okay. Propellant tank we have meter cube as the volume. The helium is regulated at a constant pressure. Pressure is given uh, 2 megapascal into the expelled from it. Okay, so this is given as the 2 megapascals. Okay, the molecular weight of helium is 4. Calculate the following. Work done by the helium to expel the hydrogen from the tank. Okay, so work done is just a change in internal energy. So, okay, so first of all, let us calculate what is the initial. Okay, so the work done is uh, okay. So the uh, this is uh, this is your PP.
Sir, the work done is equal to the change in internal energy when the system is in adiabatic condition, I guess.
So we can assume this thing as a adiabatic condition, right? So nowhere we have it is not written that there is a heat loss or heat loss from the system, right? So we can assume that this is a
Yes, sir.
adiabatic system. Okay. So first of all, let us calculate what is the mass that is stored inside the system. Um, okay, I think that is probably the work done is just PP into VP, right? So this is
Yes, sir.
0.2 into the this is 2 into 10 to the power 6. So 4 into 10 to the power 5, or 4,400 kilojoules. Okay, that is right now. And if you
Yes, it is right, sir.
okay, then what we can do is we can calculate what is the mass. So that is, this is ppvp by T naught.
Sir, why didn't we do like 30 minus 2 megapascal? Like
Uh,
delta PV
so
can del.
no, no.
Yes, sir.
So the work done that we are doing on the system is, so we are just expelling this liquid from this tank, no? So this is done at 2 megapascals.
Okay, okay, understood, understood, sir.
Understood? So yeah, and the volume that is being displaced it is this 0.2 meter cube. Okay. So yeah. So if you have any other question, please let me know. Uh, yeah. If not, then we'll close the session for
Sir, I
today.
have one
Ah,
more. Sir,
yeah,
I have one more.
yeah.
I have
Please,
one
please
more.
go ahead, please. So it was asked in megajoules, right? So it would be some.
Yes, so the question goes like this, sir. I just put it in the chat box.
Hasn't topic is helium. So this is the same
So
follow-up question, right?
I usually get confused in this type of questions where there is an reversible and an irreversible process. So could you just clear mind out what's a reversible and irreversible process and how it is related with isothermal
So
and
whenever we
iso.
talk about reversibility, we say that the entropy change across the system is zero. Okay. So okay, let me So this is a reversible. Irreversible, civil, we have change in the entropy, and it yeah, the entropy will increase. So along with this, if the heat transfer is zero, okay, if the heat transfer is zero, it is known as adiabatic system. Okay, and along with these two conditions, it is isentropic. Okay,
Yes, sir.
adiabatic and isentropic process. Oh yeah, so this is a adiabatic and isentropic process. So uh, other helium. Okay, isentropic expansion of helium and isothermal. So isothermal, it means the temperature is not changing. Okay,
Yes, sir.
so the helium are reversible process. So the process is irreversible. So if whatever we are saying here is, so in real case there will be some of the heat transfer that will be there to the surrounding, right?
Yes, sir.
Okay, because helium will be at a lower temperature. Okay, and the temperature at this point will be higher, so there will be some temperature difference and you will have some heat loss. And also while when you are passing the fluid, okay, so there can be some irreversibilities in terms of friction within the flow, right? And it is passing through the pipe. So all these cases, when we neglect, we say that it is a isentropic and adiabatic process.
Okay, sir.
Okay, so okay. So yeah. So any other doubt?
So, like, will the mass of helium be same or different?
Okay, let us think intuitively. So if the irreversibilities are more, so yeah, it depends on the process actually. It is a polytropic, so it will not be a adiabatic. It will not be an isentropic process where your gamma is one, just will be equal to 1.67. Okay, so it will change. So for gamma for polytropic process will be different. Okay, so based on that, you can say either the mass will be higher or it will be lower. So if the gamma is for a polytropic process is sorry, so it will be usually will be less than 1.67. So the mass that will be required will be less, because let us look into that. So we are saying that there is the temperature change. Okay, so some of the heat is getting into the system, due to which the helium will boil off. Okay, and it
Yes,
will
sir.
again increase the pressure. Okay, so therefore the amount of that helium is required will be less.
Okay, sir.
Okay, so so in you can look into this in this way also, or when you look into a physical process, that is also fine. Okay, so any other doubt?
Yes, sir. 1 minute.
uh,
Yes, sir. No other doubt, sir.
okay, okay, yeah. So if you don't have any doubt, if you guys don't have any doubt, so we'll close the session. Okay, so yeah, thank you all.
Thank you, sir.